Hey everyone, it's John, and today we're going to continue on the BGP video series. So if you remember from the previous video, we just discussed route reflectors. Now what route reflectors do is they effectively circumvent the IBGP split horizon rule, which states that routes learned from an IBGP speaker will not be re-advertised to another IBGP speaker, and the purpose of that is to prevent loops. Now what route reflectors do is they bend that rule completely. If a node is configured, in the case of router 1 here, as a route reflector, if router 6 advertises a prefix to it, it will reflect out to clients and non-clients alike. Now, the issue is, if you remember, that once we do that, once we rely on a central node to relay all of our prefixes to all the other nodes in the network, we have introduced a single point of failure, and that could be a critical failure if we happen to lose that node. What I'm going to do here is to show you how to do route reflection so we get that scalability, but also build in redundancy and fault tolerance by introducing BGP route reflector clusters. Now what the clusters do is they act as one unit, each reflecting all these routes out to all the clients. Now what you need to do though is the way we configure this, right? Well, let's discuss. It would be better to discuss what happens. So let's say in the case of router 9 we inject a prefix. It goes across eBGP. Router 8 now advertises it to router 2 and it's router 1 as well because it's connected to both. But let's just say advertise it to router 2. Now router 2 is configured to be a route reflector. Now what it's going to do is going to reflect out to here across this link, here, here, and here, but also it's going to pass it to its peers of 1 and 4. Now if they're configured to be in the same cluster, what's going to happen is whenever router 2 reflects that prefix, it's going to tag it with its cluster ID of 37. Now if router 1 and router 4 are both also configured as router ID, or rather cluster ID 37, whenever it gets that prefix with the cluster 37 tag, it's going to drop it. So what that prevents is stopping it from advertising here and reflecting it and reflecting it and reflecting it, so on and so forth. We have the cluster ID and the originator ID, which is for loop prevention within a route reflector topology. So let's discuss how this is going to work. What I'm going to do here is on the left hand side we've got topology 1, which is AS37, and on the right hand side we've got AS91. On the left we've got OSPF running on all of these nodes here, all of them, and each network, all the shared networks are advertised into OSPF as well as each router's loopback. So we've got router 6, which has got a loopback of 6.6.6.6, router 7's got a loopback of 7.7.7.7, 1's got a loopback of 1.1.1, you get the idea, and they're all advertised in OSPF, thus each node can basically ping all the loopbacks within the network here. What we've also done is, in the case of router 8 and 5, we have these connected networks, gigabit 00 and gigabit 03, sorry. And what we've also done is redistributed them into OSPF using a route map so that every node in the network can reach the next hop of here and here, so that we meet that next hop reachability criteria within BGP. On the right hand side we've got the same kind of deal, just to mix it up a little bit. Rather than use OSPF, I've ran ISIS. It doesn't matter, it's just for the point of the demonstration. The same thing is going to happen here. The difference is on this topology, this network, we're just going to have one route reflector, which is going to be router 9. Same thing again, this network here is going to be redistributed into ISIS, and this network here is also redistributed into ISIS. I'm going to run IBGP on top of that, and eBGP here, eBGP here. So without further ado, I don't want to get into it too much, I would just rather demonstrate what's going to happen. What I will say is that at first we're not going to configure these 3 route reflectors to be in the same cluster, and we're going to observe the behaviour before and after we do that configuration. So let's kick on and do it. So what I've got here is 2 basic templates. This one here is just going to be put into each route reflector, and it's going to configure the general clients. So let's go to router 1 and just paste this in. We'll do enable configure terminal and paste this in. Okay. Router 2, enable configure terminal. Let's paste this in. And all we're doing here is pasting in all the commonalities. Now, from the point of view of router 1, we've configured 6, 7, 8, 3 and 5, each to be a peer and each to be a route reflector client. However, we've not configured the peering of router 2 and router 4. So let's go into router 1 and do that now. So we'll do neighbor, all the 2s, remote, and our AS is 37. And neighbor, all the 2s, update, loopback 0. And let's go and do number 4, remote 37, neighbor, all the 4s, update source, loopback 0. Now let's go to router 2 and do the same thing. We've configured all the client configuration. I'll just show that here. So you can see that all the clients are configured, but we still need to peer with 1 and 4, just like we did with number 1 there, peering with 1 and 2. The difference again is that we don't make these route reflector clients, we just make them normal peers. So network, or rather neighbor 1.1.1, remote 37, neighbor 1.1.1, update source loopback, and let's do number 4 as well. Okay. Now let's go to the bottom one, which is router 4. And we're going to have a neighbor relationship with router 1 and router 2. Again, not a route reflector client configuration, just a normal BGP peering. So neighbor 1.1.1.1, remote 37, neighbor 1.1.1, and our update source is our loopback of all the 4s. And we're going to do remote 37, neighbor. Okay, so what I'm going to do now is go to each of the peers. Now remember, the whole purpose of route reflectors is to prevent us having to configure a full mesh. So all we need to do is for each node, they just need to peer with the route reflectors. So number 6 is to peer with 1, 2, 4, 7 needs to peer with 1, 2, 4, 8 needs to peer with 1, 2, 4, 3, 1, 2, 4, 5, 1, 2, 4. So I've got that configuration here in a basic template, peer with 1, 2, 3, 4, and we'll just paste that into all of the clients just for brevity. So let's go to number 6 and we'll do configure terminal router BGP 37, paste that in. Number 7 router let's go to number 8. And the last two is 3 and 5. So let's go here. Enable configure terminal. And number 5. There we go. So we should now establish our peering with 4, 1 and 2. Yeah, that's us. Okay, so we've now configured all of our IBGP within here. What I'm going to do now is configure our eBGP across this link and across this link. So let's go here. And we'll just do neighbor 200.0.0.2. We're just peering on the physical interface. And let's complete that peering by going to number 9. And we'll do enable configure terminal router BGP 91 neighbor 200.0.0.1 remote 37, and we should get our eBGP relationship coming up. There we go. And let's just copy that configuration down here. So we'll do neighbor 201 this time, 0.0.2, and remote 91. And here, enable conft router BGP 91 neighbor 201.0.0.1 and remote 37. We should get our eBGP peering coming up. Okay, so now, like I say, on this router here, or rather this network, we've got ISIS and we have redistributed our connected networks as level 2s, so we have reachability. So let's go and configure IBGP on top of that. Now in this case we're just going to configure number 9 to be the route reflector, so let's do enable conft router BGP 91, and we'll do neighbor all the 12s and remote 91, neighbor all the 12s, update is loopback, and neighbor all the 12s route reflector client. And let's do the same with the 13. Okay, now from the point of view of number 12 and 13, they only need to pair with number 9. They don't need to pair with each other because we're using route reflection. So let's go and do that just now. And we'll do it neighbor all the 9s, remote 91, neighbor all the 9s, update source, loopback. Should get our peering coming up. There we go, took its time. And we'll do configure terminal router BGP 91, neighbor all the 9s, remote 91, neighbor all the 9s, update. Okay, so what I'm going to do is go on to router 13 and inject a prefix into BGP. So let's go and create another loopback, and we'll just call it what, loopback 44, make it nice and visible, all the 44s. And let's go into router BGP 91 and we'll just advertise it into BGP. Okay, we're now injecting that into BGP. Let's have a look at router 9 to see if it's received it. Not yet, it's clear IPBGP soft. Still taking its time here. That's strange. That one's got it. Hey, just taking his time there. Okay, so let's go across to router 8 and see if it's got the prefix. It does. Now what I want to see, or rather what I want to show you rather, is what happens here, because remember we've actually not configured these route reflectors to be in the same cluster. So let's have a look at this one here, and we're going to see it's going to learn it from 4 sources. Okay, show IPBGP, we can see it here. Now where it's going to learn it from, it's going to, well, this prefix has been advertised across here, okay, so it's going to learn it from router 8. It's also been sent across here, so it's getting learned via router 5, so it's learning it from 2 sources, which is 8 and 5. But router 2 is also learning it from the 2 route reflectors. It's also going to learn it from 1 and from 4. Now, if you remember what I was saying, is that the route reflector should be dropping it. Well, not yet, because they're not configured in the same cluster. So what I'm going to do is, if we actually look into number 2, and we do show IPBGP, we're going to see that, right? We are learning it from 5, which is down here. We're learning it from 4, which is a route reflector. We're learning it from 1, which is also a route reflector, and we're learning it from 8, which is up here. So what's happened? What we need to do effectively is configure all of these to be in the same cluster, and we're going to see what happens. So here's how to configure them all in the same cluster. We'll do router BGP 37 and BGP cluster ID. Pick a cluster. You can do it in the kind of IP address format, you know, like 1.1.1.1, or just give it a basic ID like 37. which is what we'll do. We'll configure this to be the same cluster, and let's have a look. And we'll do BGP, or rather router, BGP 37, BGP cluster ID 37, and let's go down to number 4 and do the same thing. We'll do BGP cluster ID 37, and let's just clear that BGP process. We'll just do it softly. Okay, so let's do show IPBGP. Now we're only learning it from 2 sources. We're only going to learn it from the point of view of number 2, we're only going to learn it from 8 and 5 now. We're not going to be getting it from 1 and 2, because when 1 and 2 reflect it to us, they're going to have the same cluster ID, so it's going to be dropped. And let's just confirm that. Okay, so you see we're learning it from 8 and we're learning it from 5. Okay, so we're actually dropping those ones coming from the route reflectors. The same is true of 4, it's only going to have 2, it will be 5 and 8. Show IP BGP, show IP BGP, and so we're learning it from 8 and 5, and number 1's the exact same. 8 and 5. Now what happens from the point of view of the clients? Well, they're going to receive it from 3 sources, and those 3 sources, can you guess, are going to be 1, 2, and 4, because they've been reflected. Oh. So let's do show IP BGP. We've got 3 sources. Show IP BGP 44. Now let's look at this. Because these routes are being reflected, we've got the appending originator ID and cluster list, and you'll notice the cluster list from every source is the same. They're all 37 now. But what you will notice is that the originator ID is 5, 5, and 5, and that is true of all the clients. So what happened to 8? I mean, it's still 8's coming in from here, from the point of view of a route reflector. 8 is still advertising, so why are we not seeing it in the clients? Well, remember from the previous video is that route reflectors will only reflect the best route it sees. So clearly these route reflectors are picking the bottom path from router 5 as the best path and only reflecting that. So if you look at all these, every one of that prefix will show the cluster ID of 37, but the originator ID will always be 5 right now. You see that? So we go here, show IP BGP, 5, 5, 5, even though it's from 4, 1, and 2, and they're all in the cluster of 37, 37, 37. So what does this actually mean though in real terms? Well, what it means is that if we happen to lose this node, we would still have 2 sources learning. So what we've basically done is we've built in fault tolerance. So if we happen to lose 2 nodes, let's say these 2 went out, all of these routers here could still learn every route from 4. If 4 and 2 went out, all of these can learn it from just 1. Basically, the only way this would be defeated would be if 4, 1, and 2 all went out, the 3 route reflectors. So that's the kind of redundancy we've built into this. Now what I want to do is quickly do a demonstration here. And remember that the best path preferred was via router 5. What I'm going to do is change the local preference so the advertisements coming across this link are now preferred, and let's just see what that does to the actual BGP advertisements. Let's go a route map and just call it pref, and we'll permit 10 and just set the local preference to 200, and we'll make the route map pref and pair 20 exit. And what I'm going to do is go into BGP and we'll do neighbor 200.002, which is this node here, this interface, and basically advertisements come from this one here is going to have the route map called pref inbound. So let's clear IPBGP soft. Okay, so the advertisement of that prefix is going to come across two sources, across here to router 5 and across here to router 8. However, the route map is now going to tag that with local preference 200 across here. So now internally we're going to prefer this path. Now what's that going to do in terms of the clients? We're now going to see the same thing. We're going to see 3 sources, but you'll notice the next hop has changed because the originator ID is going to be all the 8s now for everyone. You see that? So the originator ID is 8s, but the cluster list remains the same. Now, that's because route reflectors are only going to reflect the best route, and because the best route is now through 8, it's only going to reflect ones originating from number 8 because 5 is not the best route anymore. So you're thinking here maybe that, well, let's say, okay, so we've got our cluster, and if we receive an update from a route reflector in the same cluster, if a route reflector does, then it's going to drop it. So what would happen if, let's say, imagine number 2 was connected to up here and this link was not, if these 2 links were not available and we were actually connected via a route reflector, what would happen? Would we not get the update to this route reflector because the route would come in, it would reflect it here, and number 1 and number 4 would see it from the same cluster and not learn it. So routes directly connected to this one would not be learned by 1 and 1 and 4. Well, no, because routes learned via here are not actually being reflected. They're kind of being originated or passed on normally in IBGP. These are not actually being reflected from an IBGP source. So what I'm going to do here is just show you that. This can be a wee bit confusing, a bit of a wrinkle in BGP with route reflectors. So let's create a loopback called, I don't know, 66, and we'll put them all in. Okay, and we'll do router BGP 37, and let's do net 66, 66, 66. Okay, so let's do show IP BGP. And we're now injecting the 66s. So clearly this is going to be available via this. Now here's the question, is it going to be available from router 2 and router 4 because it's coming from router 2? So let's have a look at that. Is it in BGP? Well, yes it is. Actually, we've got a rib failure there, which is, have I maybe, I think I might have put that in OSPF rather. I think I might have redistributed that because I changed that. Just effectively, let me just show you that just so you know. If we look at this, the rib failure means it's not actually being preferred by BGP. So if we do a show IP route, let's have a look. Yep, see that? We've got it in here, but it's being learned by OSPF, which is going to have a lower AD than IBGP, which is obviously an AD of 200, whereas OSPF is 110. What I think I've done here is I was going to change the demo for I ran this, and I think I've still left on the redistribute connected subnets on this, so I'm redistributing that into OSPF when I shouldn't be. I've done that, so basically I'm redistributing that into OSPF, so it's preferring the OSPF route. Let me just change that, so let's do a router OSPF. Just ignore that, we don't need to worry too much about that. No redistribute connected subnets. Okay, so that'll be changed, and now let's do it now. Show IP BGP. Yep, those R's have gone because now show IP routes. Yep. That's gone. Right, okay, so as you notice, right, because we've actually injected it via, we've actually advertised it here, we're not reflecting this route. So it's not going to get the actual route reflector tag. So if we do a show IP BGP, so let's look at this here. You'll notice we don't have the originator ID in the cluster list because it's not actually a reflected route. So if it's not a reflected route, it's not going to see the cluster ID, so it's not going to have that mechanism where it sees the cluster ID and drops it. So let's just say this router here was directly connected to this router and this one didn't exist and this didn't exist. We could still learn routes through the route reflector because it's not a reflected route. Now, I know that might sound like a bit of a kind of a head wasting concept, but it's really not. Only routes which have been reflected, in this case, we're learning it via here and here. So this route is coming in and being reflected, therefore it's going to have the cluster ID and the originator ID appended, and then it will be dropped. If the route is just learned via this router, i.e. not learned via another IBGP source and reflected, it's actually learned directly from this, it's not going to append the cluster list and the originator ID, therefore it's not going to be dropped. So you don't need to worry about not learning routes because they're on the same cluster. That will only happen with IBGP speakers, and they should all be fully meshed anyway. So when it's not going to reflect that, it doesn't matter because it will learn it from the original source. Okie doke. So I understand this can be a confusing concept if you're just new to route reflection and clusters, but trust me, the best way to deal with this is to lab it. So I think what I'm going to do is end the video here, and the next one we're going to do will be on similar IBGP loop prevention and with scaling out that loop prevention, and that is using BGP confederations. Okay doke, so that's the end of the video, and lab this one up, and I'll see you guys soon. Thanks very much, bye bye.